Welcome back on series of lectures on microprocessor and microcontroller. And myself, Rajakishore, Assistant Professor, Department of ECE, Mari Lakshman Reddy Institute of Technology and Management. In our last video, we have discussed about the basics about 8086 microprocessor and the where microprocessors are used and the various applications of the microprocessor. So just we recall once the definitions of the microprocessor once again. Microprocessor is a multi-purpose programmable device that accepts the digital data as an input, processes it according to the instructions stored in the memory and provides the result as an output. So this is one of the definition from one of the textbooks, but as per the perception, the definition may changes or definition may define as a. So in some cases, some other persons have defined as a processor like this. A microprocessor is a multi-purpose, programmable, clock-driven, register-based electronic device that reads the binary instructions from the storage device called memory, accepts the binary data as an input, and processes the data according to the instructions and provides result as an output is another definition about the microprocessor. So let's go into the today's topic or today's lecture. Today we are going to discuss about architectures of 8086 and the various modes of operation of 8086. So before raising a question that how do I define a process? So because we have seen that many number of stages and number of people are saying that it is an 8-bit processor, 16-bit processor, 32 or a 64-bit processor. So based on a registers set in the processor, we can define our processor. We can define the how many bit of that particular processor. For example, if I take a 16-bit processor, I can say that has a 16 data lines and all the registers are 16-bit in long. It indicates that a processor is defined size of the bits or size of a data bus capacity. For example, one more take, if I take a 32-bit processor, which indicates that it is having obviously 32 data lines and all the registers are in 32-bit long. So, but in case of comes for the 8086, it is having a 16-bit data bus and 20-bit address bus, which indirect manner indicating that 8086 can address up to 2 power 20 can approximately can take as a 1 megabyte of memory. So when we going to start about an architecture of 8086, we need to know different architectures available. So we know that we have two different architectures like hardware architecture and Van Neumann architectures. So 8086 uses Van Neumann architecture. Why? Because we are using one single memory, like 1 megabyte of memory is utilizing for both program and data memory purpose. Then what is hardware architecture? So in case of if this memory is divided or separated as its separate memories. For example, if you see in the diagram hardware architecture, it is using two separate memories for data as well as programming. And if you come for some of an advantages of Van Neumann architecture, you can say that a single address and data bus is sufficient to transmit a program or data memories. But in case of hardware architecture, it is not so. It requires a two separate or individual buses for the data memory as well as the program memory independently. When you come for the Van Neumann architecture, the designing of Van Neumann architecture is little bit simple because of required data buses are one, whereas in case of hardware architecture, it is little bit complex because of two separate buses. So without wasting our time, let's go into the details of 8086 architecture. Before starting an architecture, let's we recall the sum of the features of 8086. Why I am recalling again these features? Because these are the concepts which we are indirect manner related to the architecture what we are going to see. So it has an instruction queue which capable to storing 6 instructions bytes from the memory, resulting fast processing. So which means that in case of 80 and 6, they introduce the concept of instruction queue called as a pipelining concept, which is introduced in 8086 onwards. So the first feature, because if a new advancement happened from 8085 to 8086, is a pipelining. And second thing, it has a first 16-bit processor. Because of 16-bit processor, we can say that the size of ALU, registers and internal bus or an external bus are in size of 16-bit only. And it is available in 3 different modes or 3 different versions based on the frequency which 8086 can operate. One 8086 simple can work call as a first thing is a 5 megahertz. If I take 80862, which is nothing but which works under 8 megahertz clock frequency, and 80861 works under 10 megahertz of clock frequency. So then it uses 2 stages of pipelining process. As we go into in-depth details about pipelining in the later section, but in case of 8086, we are going to use 2-stage pipelining called as a fetch stage and execute stage. Because of this pipelining process, the improvement is happened, which means that execution time is faster compared to the previous versions of the processor. And the fetch stage can use to fetch of 6-byte instructions and store them in a queue. As we discussed in the first point, because the instruction queue is capable to store a 6-byte of instructions. And it is having a 256 vector interrupts. Because if you compare with an 8085 microprocessor, it is having only 5 interrupts. That too, those are defined interrupts. But here it is having a 256 vectored interrupts. In few are defined and other things are left for the programmer to utilize. They utilize to write his own interrupts. And last point, as we said that because it consists of a whole 2900 transistors used to fabricate. Yeah, now we'll see in-depth details of architecture of 8086. So this is an entire block diagram of 8086. So let's for comparison, I have larger size this one. So in-depth details will go. So this is an architecture of 8086. This is architecture consists of are separated as 2 blocks. So let's understand each block. The first block is called as a bus interface unit. The main aim of the bus interface unit is to fetch the instructions, read the data from the IO ports and write the data to memory or IO ports. So what it means, exactly what bus interface unit is doing is just fetching an information from a memory or an IO devices for a read operation or write operations. Only task take the information from memory or an IO devices. And the second one is called as an execution unit. So this execution units execute the instructions that already has been fetched by bus interface unit. Okay, what execution unit? It is going to perform only execution task, and from where it will be execute the instructions, where the instructions is already fetched by the bus interface unit. And these both unit, like bus interface unit called simply BIU and execution unit called as a simply EU, will work independent separately or independently, which means that there is no relation between these. When bus interface unit functioning or taking some data from the memory, simultaneously processor or execution unit execute some task. So these two units are functions separately. So let's go in depth details about bus interface unit. So as we said that bus interface unit provides an of interface of 8086 to an external world like an external memory or an external IO devices via a system bus. As the system bus here specifies that as we already discussed this 8086 having a three buses data address and control buses. So this bus interface unit is the main function to interface 8086 to an external memory or an IO devices. So then it's perform a various mission cycles, which means that it need to be generate various mission cycles for reading operation and writing operation that may be from the memory or an IO memory, okay, and transfers the data between in memory or an IO devices. So these are some of the following functions. As I said that 8 generate a 20-bit physical address from memory access. It fetches the instructions from the memory. It transfers the data to and from the memory and IO devices and maintain 6-byte prefetch instructions are a queue supporting called as a pipelining concepts. And the main things, this main bus interface unit consists of a segment registers, instruction pointers, and an address generator circuit or address decoder circuit. Let's go in depth details about these are following blocks. Yeah, bus interface unit. If you take segment registers, it is having a 4 segments like a code segment, data segment, stack segment, and extra segment. So this is a how the segments will be an address. So what is this? How it will be? Because 8086 having 1 megabyte of memory, which is divided as a parts or as a segments, each can size up to a 64 kilobytes. So 8086 can directly address these 4 segments of totally 256 kilobytes. How it 256 will comes? Because as I said that it is divided as a 4 segments, each of 64 kilobytes, 4 into 64 is 256 kilobytes of within the, so which indicates this particular point tells that I can interface or I can access directly 256 kilobytes of memory at a time, and the programs uptime to access code and data in the segments by changing these segment registers content to a pointer to a desired segments. Okay, so this is nothing but again dedicated address, because as I said that it is having a 20-bit address generator. So what this address generator will do? This is an address generator block. I'll show here. This is our address generator. This address generator main aim is convert a logical address which is generated by a internal segment registers and an instruction pointer, converts those logical address into an actual physical address or an effective address of 20-bit size. Because as we have divided as a segment of 16-bit each, so these two 16-bit addresses are used to generate 20-bit address that can be taken care by this address generator. So in depth how it will going to be generate a physical address. So it takes that segment register address into 10, which is 10 is nothing but simply I can say that I am going to logical shifting left shifting of 4 bits of a segment address that may be a code segment, data segment, stack segment, or an extra segment, plus an offset address. It is maybe in an instruction pointer or one of the some of the register holding an offset address. So actual physical address can be calculated as a segment address into 10 plus an offset address. In the preceding slides we'll see some of an example further. So as we said that a segment registers is classified as a code segment, data, stack, and extra segment. So then we'll see further for segmented memory, which means that how this 1 megabyte has segmented. So this one memory of 8086 or 8088 based system organized as a segmented parts. The CPU of 8086 can able to address of 1 megabyte of memory location. The complete physically available memory may be divided into the number of logical segments called as a segments. So assume that this is your 1 megabyte of location, okay, which is starting address from 00 to ending address of FFF. Now this 1 megabyte of address as divided as a code segment here, one which is size of 64 kilobyte, and data segment 64 kilobytes, stack segment, extra segment 64 kilobytes, and star segment. So you may have a doubt, after the 4 segment what about the other memory, which means the other memory can also use for the segment registers as a segment registers, but at a time I can able to access only 256 kilobytes of memory only. So as I said that each segment of 64 kilobytes in size, a segment may be located anywhere in the memory. As we see in the diagram previously, that segment is not fixed in one memory. It may be run entire, or it may be chosen available 1 megabyte of location anywhere. Each of these segment can be used for the specific functions. Like code segment is used for the code, data for the data, stack segment for pointing the stack. And likewise, individual segment registers are you going for to use for the specific functions. So code segment used to store the instructions, which means that write the code, write your program, that I'll go for a code segment. Stack segments are used to as a stack and store a return address, mainly when I want to be use any push and pop applications for instructions, stack segment going to be used. Data and extra segments are used to store the data bytes, which indicates that if I'm write a code, particularly if I want to have some huge amount of input data, so this input data is being written into your data segment, okay, or this extra segment, whereas the code has to be right in your code segment memory. So this way individual segments can be used for the specific functions or a specific task. So that 16-bit consists of a segment by actual point to storing a practical segment. So these segments may overlap or not overlap. So here the question is nothing but each segments will be overlap or non-overlap, which means that a code segment maybe starts. So the next diagram, yes, here we're going to see how two 16-bit registers are used to calculate a 20-bit address. Okay, let's take a 1 megabyte of memory and let's assume my code segment is pointing 1, 2, 3, 4. Example I'm taking. So from this it is going to be access, okay, 64 kilobytes in your available physical memory. But actual address of the code segment is 1230H. Why? Because as I said that the last higher upper bytes of the data as shifted, or it's shifted to a 4-bit left shifting is multiplied by 10, so that this code segment actual address is 1234. And as I said that it can be added with a offset value, so that assume that I am having an offset address in my instruction pointer of 0568. So total, if I'm getting actual physical address which my pointer is pointing to 179p8. But actually 64 kilobyte I can access from the location of 12340 to 2233F. This is an actual physical address I am available. Because of an offset value, it is pointing to somewhere 179B8. This is an address where some data will be there, then it will be data will be. So this is a manner I can able to calculate a 20-bit actual 20-bit address using my two 16-bit registers. Again, I'm reminding formula once again. Code segment into 10 plus offset address. So here my offset address I'm considering is total. I can get my physical address. Okay, this is a formula, easy understand, to get your 20-bit actual 20-bit. So this is a diagram indicating that, as I said, that the segment registers can be overlapped. In this particular, this segment 1 and segment 2 is non-overlapped here, but here it is overlapped. Okay, yeah. Then what is this instruction pointer? So it is a 16-bit register again. It holds the offset of the next instruction. Okay, it holds an offset address of the next instruction of your code segment. Because of this reason only we have taken instruction pointer as a offset value in the previous example. Next, instruction pointer increment every instruction byte is fetched, which means that it's going to be automatically incremented after every instruction byte is fetched. So instruction get a new value whenever a branch instruction occurs. What it means? Because when the instruction pointer is sequentially, it is increasing when I'm executing any point. But when I want to execute any branch instruction, the instruction pointer gets complete new address from the branch which is specified, which means that it is not incremented. For example, at this point, I'm taking instruction pointer 2000 is pointing. When I'm going for the next instruction, it goes to be 2001. But if that next instruction is a some branch instruction, this is transferred to completely instruction pointer gets to a new address, something example taken as a 5000 location. So the code segment is multiplied by 10 to get a actual address as a code segment, which is, as I said that earlier, and this is a address of the next instruction is calculated as code segment address into the 10 into the instruction pointer. This is a formula which used to calculate to get an actual physical address or an effective address. So this is an example again I have given here. So what is instruction queue? Okay, so instruction queue is nothing but, as we said that I'm using concept of pipelining. Okay, this instruction queue is used to